Welcome to the next lecture on derivatives. So, in the last lecture we learned two important theorems, which are the Rolle's theorem and the mean value theorem, and then we saw one application of the mean value theorem by proving that if a function is differentiable in an open interval and is 0 in the open interval, then the function must be a constant. Today we will see some more applications, like what happens if the derivative in an interval is strictly positive or strictly negative. So, let me write this as theorem. The theorem is, suppose f from a b to r is a differentiable function so then if the derivative f prime x is greater than 0 for all x in the open interval a b, then f x is strictly increasing on the open interval a b, and if f prime x is negative for all x in the open interval, then f x is strictly decreasing. On the whole interval a b. We have seen the converse, that if we have a differentiable function and if it is increasing, strictly increasing, then the derivative is positive, and if it is strictly decreasing, then the derivative is negative. Here we are saying that the converse is also true. So, the proof is again using the mean value theorem. So, suppose we take any x 1 and x 2, then we have to show that f of x 1 is strictly less than f of x 2. So, then f is continuous on the closed interval x 1 x 2 and is differentiable on the open interval x 1 x 2. So, therefore, by the mean value theorem, there exists some c in the open interval x 1 x 2 such that we have f of x 2 minus f of x 1 by x 2 minus x 1, this is equal to f prime at c. But we have assumed that the derivative is strictly positive on the whole interval. So, this we know is strictly positive, and this implies f of x 2 minus f of x 1 is positive. This is because here x 2 minus x 1 is positive. So, f of x 2 is greater than f of x 1 whenever x2 is greater than x1. The second part is similar. So, now let us try to use this to prove some inequality. So, problem, prove that sin of x is always less than equal to x for all x greater than equal to 0. So, we want to prove that sin of any positive x is always less than equal to x. So, we can let f of x to be the function x minus sin x, and then proving that sin of x is less than equal to x is same thing as saying that we have to prove that f of x is greater than equal to 0. So, let us see what is f prime of x. So, then the derivative f prime x is equal to 1 minus derivative of sin x is cosine x, and we know that cos of x is always less than equal to 1. So, this is greater than equal to 0. Since cos of x is always less than equal to 1. So, what we have is that the derivative is greater than equal to 0. Therefore, f of x is an increasing function. So, note that in the previous theorem, if we assume that the derivative f prime x is greater than equal to 0, then instead of strictly increasing function, we will get that f of x is an increasing function, that means non decreasing function, because we have this f prime c is greater than equal to 0, then we have f of x2 is greater than equal to f of x1. So, we will use that. This f of x is an increasing function. Also, if you put x equal to 0, f of 0 is 0 minus sin 0 is equal to 0. So, therefore, for x greater than equal to 0, we must have that f of x is greater than equal to f of 0, since f is increasing function, but this is equal to 0, that is x minus sin x is greater than equal to 0, that is sin x is less than equal to x for all x less for all x non negative. Of course, this is not true for x less than 0. Similarly, let us prove another inequality involving tangent of x. So that x is less than tan x for all x in the open interval 0 to pi by 2. So, again we do the same thing, we put f of x equal to tan x minus x, and we have to show that in the open interval 0 to pi by 2 f of x is strictly positive. So, we calculate the derivative. So, then f prime x is equal to derivative of tan x gives me secant square x minus derivative of x is 1 and secant square x minus 1 is tan square x, and we know that tan x is, this is strictly greater than 0 for all x in the open interval 0 to pi by 2, because tan of x is 0 only in the integer multiple of pi. So, in the open interval 0 to pi by 2, tan of x is always positive. So, f prime x is greater than 0, therefore, f x is strictly increasing on the open interval 0 to pi by 2. This implies that f of x must be greater than f of 0, and what is f of 0 is tan 0 minus 0, which is 0 for all x in 0 to pi by 2, that is tan x is greater than x for all x in 0 to pi by 2. We will do one more problem. Problem 3 is prove that mod of sin x minus sin y, this is less than equal to mod x minus y for all real number x y. So, to prove this inequality, we note that if I take f x equal to sin of x, this is continuous and differentiable everywhere. So, we can apply the mean value theorem. By the mean value theorem, given any x less than y, there exists some c in the open interval x to y such that f prime of c is equal to f of y minus f of x divided by y minus x, that is sin y minus sin x divided by y minus x is equal to the derivative f prime at c, but f of x equal to sin x. So, f prime c is cos of c. So, this implies that if I take modulus mod of sin x minus sin y divided by x minus y, this is equal to mod cos c for some c, and we know that cosine theta in mod absolute value is always less than equal to 1, and this implies that mod sin x minus sin y, this is if x is not equal to y, this is less than equal to mod of x minus y. and of course, if x is equal to y, then both left hand side and right hand side are 0. So, this is true for all x y. So, before seeing some more application of Rolle's theorem or mean value theorem, let me do one more important theorem about continuous functions. So, this is known as the intermediate value theorem. In short, we will write IVT. So, here the assumption is, suppose f from some closed interval a b to R be a continuous function, and let y lie between f of a and f of b. So, what we have is there is a function, continuous function, and we have, this is my f of a, this is f of b, and suppose there is some y which lies between f of a and f of b, then the conclusion is that there exists some x here in the interval a b such that f of x equal to y, then there exists at least one x in a b such that f of x is equal to y. So, here we can assume that this f of a is either less than f of b or f of a is greater than f of b. So, either we have this or we can have f of a is bigger than f of b, and then if I take any y here, then again we have some x such that f of x equal to y. So, the theorem is intuitively clear. So, if you see, if we have any continuous function, then it must take, this is called intermediate value theorem, that because it takes all the intermediate values between f of a and f of b if we have a continuous function. But we will skip the formal proof. You should note that continuity is required. Note that continuity is required for the intermediate value theorem, because otherwise we can have if we allow a discontinuous function, then I can have a function like this, this is my A, this is B. Now, if you see I have f of A here, f of B, and if I take any y here, then there is no x for which f of x is equal to y, because either f of x is less in this interval or f of x is here. Right. One corollary to this intermediate value theorem is that suppose f is a continuous function on a closed interval a b, and assume that f of A and f of B are of opposite signs. That is, the product f of A times f of B is negative, then there exists at least one x in the open interval a b such that f of x is equal to 0. This is like if I have, say, f of A is negative and f of B is positive, then what it says is that if I have a continuous function, then it must cross this x axis at least once. So, this is the point x here where f of x is 0. And this clearly follows from the intermediate value theorem, because 0 lies between f of A and f of B. So, since 0 lies between f of A and f of B, by the intermediate value theorem, there exists x in a b such that f of x is equal to 0. Of course, this x cannot be a or b, because f of A and f of B are non-zero. So, there is at least one x, and you can have more than one x as well. So, this function can be like this. So, this intermediate value theorem is again very important. So, some applications of intermediate value theorem. So, the first one, let me write this again as a theorem. So, this theorem says that every polynomial of odd degree must have at least one 0. Note that one that is if p of x is equal to a 0 plus a 1 x plus a n x to the n, where n is odd, and a n is not equal to 0, then there exists at least one C real number such that P of C is equal to 0. Remark: the result is not true for even degree polynomials. For example, if I take p x equal to x square plus 1, this has no real zeros. We know that x square plus 1 is always greater than equal to 1 for all real x. So, this cannot have a 0 in R, but for odd degree polynomial we claim that there is at least one 0. So, the proof of the theorem so we have p x is equal to a 0 plus a 1 x up to a n x to the n. Since n is an odd integer, if we look at the limit of x to the n, the highest term, this as x goes to positive infinity, this is equal to positive infinity, and the limit as x approaches negative infinity, this will give us negative infinity. Right. This is because n is odd. If n was even, then both these will be positive infinity. So, therefore, if we look at this polynomial, therefore, p of x must be negative at some x and positive at some other x. Right, this will depend on the sign of this a n. If a n is positive, then p of x will approach positive infinity as x goes to infinity and negative infinity as x goes to negative infinity. That means that if you take x large enough, then p of x must be positive, and if x is large negative number, then p of x must be negative, and if a n is negative, then you have the other way. So, then by the intermediate value theorem, by the corollary to intermediate value theorem, P of x must be 0 at some point x. So, this is a very important result, that any polynomial of odd degree must have at least one real 0. That means that this must cross the x axis at some point. So, now let us look at one problem. So that x to the 5 plus 4 x minus 1 equal to 0 has exactly one solution in R. So, first of all, if we see that, let P of x be this polynomial x to the 5 plus 4 x minus 1, since P of x is an odd degree polynomial, P of x equal to 0 has at least one solution. This we know, because this is odd degree, it has at least one solution. What we want to show is that there is exactly one solution, that means that we cannot have other solution to this. So, suppose there are two solutions, x 1 less than x 2, then what we have is P x 1 is equal to 0 and P of x 2 is also 0. So, by the Rolle's theorem, note that because we have polynomial, this is continuous and differentiable everywhere, and at the end point x 1 x 2 these values are same. So, by the Rolle's theorem, there exists some c in between x 1 and x 2 such that P prime of c is equal to 0. But if we look at P prime x, the derivative here is 5 x to the 4 plus 4, and we know that x to the 4 is always non-negative, this is always greater than equal to 4. So, therefore, we get a contradiction. So, the contradiction is because we assume that there are two solutions x 1 x 2. Therefore, P x equal to 0 has exactly one solution. You might ask question that where is the solution? I mean, what is the solution? So, note that here we have a polynomial of degree 5 So, there is no general method to find the roots of this polynomial, but what we can do is that we can try to use the intermediate value theorem to find approximate solution as follows. What we have is, we have p of x is equal to x to the 5 plus 4x minus 1. So, note that if I put x equal to 0, p of 0 is equal to minus 1, this is negative. If I put p x equal to 1, then I get this is equal to 4, which is positive. So, by the intermediate value theorem, we know that p of c is equal to 0 for some c between 0 and 1, right. So, you have to look for the root of this polynomial only in the interval 0 to 1. There is no other root. So, there is no 0 outside this interval. Now, what you can do is that if we look at the midpoint, the value at the midpoint, which is half. So, if you see p half, this is equal to 1 by 32 plus 4 times half is 2 minus 1. Now, this is again, this is 1 plus 1 by 32. This is still greater than 0. So, now you know that p of 0 is negative, p at half is positive. So, there must be, so since p 0 is negative, p half is positive, the 0 must lie in the interval 0 to half. Again you can repeat this process, again find what is p of 1/4. P of 1/4 will be 1 by 4 to the 5 plus 1 minus 1. So, this is 1 by 4 to the 5, again it is positive. So, the 0 must lie in 0 to 1/4. Then you can find at 1/8 what happens, and if at 1/8 p of 1/8 this gives 1 by 8 to the 5th plus half minus 1, and this is equal to 1 by 8 to the 5th minus half, which is of course negative. So, therefore, the 0 must lie in the interval 1/8 to 1/4. Previously, we had that the 0 is between 0 to 1/4. Now, we divided into subinterval 0 to 1/8 and 1/8 to 1/4, and we know that the 0 must lie in 1/8 to 1/4. Again, you can take at the midpoint of this interval, and this way you will get a better and better approximation. So, proceeding this way, we can get the 0 lying in smaller and smaller interval. This method that we used here is called the bisection method. Because we subdivide the interval into half and half, and then we see in which interval the 0 lies. So, this gives one method to find the where the 0 of a function lie. Let us do some more problems. So, prove that cos of x is equal to x for some x in the open interval 0 to pi by 2. Right. So, note that there is no general way of solving this equation cos x equal to x, but still we want to prove that this has some solution in this interval 0 to pi by 2. So, to do such problems we use the intermediate value theorem. So, you write let f of x be equal to cos x minus x, and then because we have to prove that the 0 of this function lie in this interval, you find what is the value of this function at the end point. So, f x is continuous everywhere. Also, if I find what is f of 0, this is cosine 0 minus 0, which is equal to 1. So, this is greater than 0. What about f at pi by 2? This gives me cosine pi by 2 minus pi by 2, which is equal to 1 minus, sorry, this is equal to 0 minus pi by 2. So, this gives me a negative quantity. So, f of 0 is positive, f of pi by 2 is negative. This means that by the intermediate value theorem, there exists some x in the interval 0 to pi by 2 such that f of x is equal to 0, that is cos x is equal to x, right. And again, like we did for the previous one, you can use the bisection method, and then you find the value at pi by 4, you will get cos pi by 4 minus pi by 4. You have to see whether that is negative or positive to determine in the interval of half of this length where the solution lies, and you can keep doing like that to find smaller interval where the solution lies. Let us look at one more interesting problem. So, we assume that f is a function defined on closed interval 0 to r, and this is assumed to be a continuous function. Also, it is given that f of 0 is equal to f of 2. The value at the end points are equal. What we have to show that prove that there exists points x and y in this closed interval 0 2 such that y minus x is equal to 1 and f x is equal to f of y. So, what we are given is we are given any continuous function from the interval 0 to 2, and only thing we know is that f of 0 and f of 2 are same. The value is same, and then we have to show that this can be any function like this. We have to show that there are 2 points where the value f of x and f of y are same, and also that this x and y differ by 1. So, to solve this, what we do is see, we have to show that to find x and y such that y is equal to x plus 1 and f of x is equal to f of y. That is, we need to show the existence of x in the interval 0 1 such that f of x is equal to f of x plus 1, because y is x plus 1 and we want this to lie in the interval 0 to 2. So, therefore, x must lie in the interval 0 to 1. So, we look for a point in 0 1 where the value of the function is equal to f of x plus 1. So, this suggests that what we do is that we will let g of x be equal to f of x plus 1 minus f of x, and this function is defined for x belonging to the closed interval 0 1. So, if x is between 0 and 1, x plus 1 is between 1 and 2. So, g of x is defined in the interval 0 1 and this is continuous. So, then g is continuous on the interval 0 1. Also, what is the value at the end point? What we have to show is that g is 0 at some point. So, we find the value at the end point, g of 0 will give me f of 1 minus f of 0 and g of 1 is equal to f of 2 minus f of 1. What is given is that f of 0 is equal to f of 2. So, this f of 2 is f of 0 minus f of 1. So, g of 0 is g f of 1 minus f of 0, g of 1 is f of 0 minus f of 1. So, g of 1 is nothing but minus of g of 0. So, thus by the intermediate value theorem, there exists some x in the closed interval 0 1 such that g of x is equal to 0. Right. These are of opposite signs. So, there is some x such that g of x is 0 and that says that is f of x plus 1 minus f of x is equal to 0, that is f of x plus 1 is equal to f of x. Hence, we are done. So, this problem again was application of intermediate value theorem, but we had to define this new function g of x and then apply the intermediate value theorem. So, we will stop here. In the next class, we will learn some more topics on derivatives. Thank you.